a flow chart for the different situations. And then we'll work through a couple of concrete examples using this afterwards. Does that sound okay to you guys? So what we're talking about in 8.8 is the possible interactions of lines in 3 dimensions. So there's 4 possible situations. Now, you remember how many situations did we have in 2 dimensions? 3. Okay, so the 3 situations are intersecting, parallel, and then coinciding. Right, you remember that from Algebra 3-4? Now, in 3 dimensions, you still have those same 3 situations. You can have intersecting, parallel, coinciding, but there's a 4th situation, and that's not parallel, not intersecting. So like the 2 lines are in different planes that are never going to intersect, but they don't have the same direction, right? So they're not parallel. They wouldn't be considered parallel because there's not one plane you could draw through them where they'd be going in the same direction, but they're also not going to intersect. So those are the 4 situations we can have in 3 dimensions. Does that feel okay there? Okay. So what I've done is we have 2 lines here. The first one R1, the second one R2. So the point vector I called R1 comma 0, and the direction vector v1, and in the other line the point vector is r2 comma 0 and the direction vector is v2. So the first thing we do is we check to see if the 2 lines are parallel. And to do that, you take the slope component of one of the equations and set it equal to the other direction, and see if you can solve for a specific t or s in that whichever situation you pick. It doesn't matter which one you choose. Usually this is pretty trivial, like you'll see a scalar multiple more often than not. So if that parallel check passes, that means that either the lines are coinciding or they're parallel. If they're not, if it doesn't pass that parallel check, they're either non-parallel, non-intersecting, or intersecting. So if we go down the yes branch, we have to check, does R1 overlap R2? So basically, if I have 2 lines that are parallel, if they have one point in common, all of their points would be in common, right? If I have 2 lines that are parallel that both contain the point 1, 2, that the 2 lines are coinciding. Everybody agree with that idea? So what we do then is we check to see if I can take the point vector from R2 and put that into, or get R1 equal to that, or vice versa. You can take the point vector from R1 and set that equal to R2. If that's possible, if R1, or if the line R1 can have the point vector R2 on it, then yes, they're overlapping. If not, then they're just going to be parallel. And if we went down the other branch, so no, they weren't parallel, we want to know, does R1 intersect R2? And to do that, we do just like what we did in 2 dimensions. We set the 2 equations equal to each other and see if we can find value of s and t that satisfy that system. If the answer is yes, then we can say that they intersect, and we can use that value of s or t to find the point of intersection. If not, then they're this new situation where they're non-intersecting and non-parallel. I think in the lessons we called that 3D parallel. That's the only place I've heard that term used, but that's the idea. So I wrote this out visually because I think that often that's helpful for students to kind of visualize what you're doing and the order in which you're doing things and what tests does what, because on the sheet of paper they look rather similar. And sometimes it's hard to keep that straight, so I wanted to start off with the nice organized version of this, and then we'll go in and look at some specific examples next to feel a bit better about doing this in practice. Is everybody okay so far? Again, speak up if we're confused on anything. Anybody still working on the flow chart that needs me to stick around here for a minute? Okay. Oops. We're into February. So again, I'm just going to go straight into some numeric examples because I've done like the lecture part already on the previous slide. And I basically condensed the lesson into that flow chart, which I think is probably going to be more useful to you, having everything kind of consolidated into one place like that. So S and T are like the parameters. Those are the independent variables that you're using to generate the points that are lying on these three-dimensional lines. Just like you have y equals 5x plus 7. You have a y and an x. Here we have an r vector and a scalar, a s or a t or whatever. So here are my two lines in 3 dimensions. And if we want to figure out how they're interacting, the first thing we'll ask is R1 parallel to R2. So to check that, I'm going to take the slope component from one of them and set it equal to that direction vector. So basically we're saying, can the direction of R1 be the same direction as R2? Is there a multiple of t that I can multiply to give me the same direction vector? And we can probably just do this by inspection, right? Everybody agree? If t is negative 1/4, that holds. Everybody agree? You don't have to show any algebra. If you just write down the value for s or t or whatever that makes it true, that's good enough for me. So yes, those two lines are parallel. Everybody's okay with that? Okay. So now we have to see does one of these lines overlap the other? So to do that, I'm going to take the point vector from R2 and set it equal to R1. You could also do the opposite. You could take the point vector from R1 and set it equal to R2. Oops. Everybody's okay so far to here? So this creates a system of equations. When I solve that system, I get the same value for t each time. So what that says is that that point vector from R2 lies on the line for R1. So those two are coinciding then. Yes?
What would the equation define if it overlap?
So I check to see if the R1 can equal the point vector from R2, or if R2 can equal the point vector from R1. Either way of doing it is fine. It doesn't matter which direction. That's what you needed?
Yeah.
Okay. Everybody feel okay? Ready to do another? So again, the idea here, or the deal with this, is the individual steps, the things that you need to show, aren't terribly complicated, but keeping track of what's going on and making sure you understand what it is that you're doing, that's probably the trickiest part of this, right? The arithmetic that I'm doing, like most of these things were things that we just did in our head, like solving for t's and stuff, was pretty easy. So here's a new pair of lines. So we're going to start the same way. We're going to check to see if R1 is parallel to R2. So I'm going to take that slope component from R1 and see if it's equal to that direction vector from R2. So here t is negative 3 over 2. Here t is negative 5 over, or 9 over 5. So no, I don't even care what the third equation would give us, or the third value of t would need to be. Doesn't matter to me. If the first two don't agree, can't be the same, or can't be parallel. Does everybody feel okay there? Okay. So now we ask, does R1 intersect R2? So to do that, I'm going to take R1 and set it equal to R2. Oops. Yes, Keith. Certainly. Everybody so far so good? I'm going to turn this now into a system of equations. By the way, this is the harder of the, or the hardest of the checks that you have to do, is the three checks. Is this, is there an intersection? It involves the most algebra. I'm going to rearrange this so that it's like kind of in standard form. So I'm going to put the s's and t's on one side now and the constants on the other. Everybody's okay with what I did there? Again, I just did some algebra in my head, but I just like added 6s to both sides and then subtracted 2 from both sides to get the variables on one side and the constant on the other. So how many variables do I have in this system? 2. How many equations do I have? Do I need 3 equations to solve for 2 variables? No. How many equations do I need? 2. Does it matter which 2 I choose to use to do the solving?
No.
No, but what do I need to still have to do? I have to check my result with the third equation. So it's possible that you can find a system for 2 of the 3 that fails in the third one. So whatever our answer we get when we solve our system, we got to make sure we go back and check. So we're going to take this system, and I'm going to solve this system just using a matrix. You could solve it by hand if you wanted to, but I like using a matrix because I can do it all on my calculator to write anything down. Do you remember how to do this? We did it the other day in class. If you did the homework set, you would have had to practice this a couple of times, or it would have been good to practice this a couple of times. It would have made doing the homework a lot faster than having to solve a system by hand. So we start by opening up the matrix menu on our calculator. Then we'll go over to the Edit tab. We'll set our dimension to 2 by 3. And then we'll type in the coefficients from our system exactly as they appear. So here's that matrix, everything all typed in. We'll then exit back out to the home screen. We'll go back to the matrix menu, go to the Math tab, scroll down to the bottom and retrieve the RREF command. Select that onto the home screen. Go back to our matrix menu, select that matrix A that we just entered in, and press Enter. The last column tells us that the first variable in our system, that would be the S, is equal to -2. And the second row tells us the second variable in our system, that's the T, is equal to +2. Yes, sir.
How do you know that the top one is
Because if you look at the first row, it's basically, I said the first column was where my S's went. The second column was where my T's went. So if I read the first row, it says 1S plus 0T is equal to -2.
Okay.
So it just depends on which order you put them into in your equation. But they have to line up. Columns have to have the same variables in them. So you couldn't put ST and then the second row T then S. That would be a problem. Okay. So let's check here real quick. If I plug -2 in for 4, if I plug +2 in for T, I get 6. 4 minus 6 is -2. So that does work. So yes, they intersect. Now to find that point of intersection, we can choose either to use the S or the T, it doesn't matter. For the sake of argument, let's pick the T. And I know that in R1, I have 2, 4, 1 plus 4, 5, -3 times 2 should give me, let's see, 2 plus 4 times 2 is 10, times 2 is 14. 1 plus -3 times 2 is -5. So my point is -5. Notice when I wrote the point, I wrote it horizontally with a parenthesis rather than vertically, like a vector, just to make sure I'm notationally describing what's going on there effectively. What do you guys think? That's kind of the hardest situation, is when that is that one, or at least the one that requires the most amount of symbolic manipulation or algebraic manipulation, is the intersecting. Questions on what we've done so far? Okay. Well, this was a rather challenging process, right? Not trivial at all. Let's have you guys take some time right now to practice using these, or using these techniques. 4 problems or 5 problems here are like 119 to 124 or something. That sounds about right. Let's double check the number. Even better. So it's okay. So let's take the remaining time in class and let you guys just kind of get to work on these things. I think it helps to have a chance to practice this stuff right away and ask some questions and get some feedback. If you want me to check what you're doing or even check your answers or anything like that, you're welcome to do that. Just come on up and bother me. Everybody sound good? Okay. Therese? 118 on the board? I just did 2 on the board. Oh, 118's the problems, right? Oh, sure. Oh, sure. Let's see. What would I ask you to do on that? Oh, okay. From the line. So I'm just going to pick some values for t, its own point. Okay, with that, Therese? And I just picked values of t that were easy to deal with. So when I plug 0 in for t here, I get -4 for the x component, since the I is just representing the x component. Well, the j component, or the y component, is always going to be 5 because it's a constant. And then the k component, or z component, is going to be 2. When I plug 1 in, I get -1. And if I plug -9. Is that okay? Yeah. So just if they're in that linear combination form, doesn't really make any difference. You're just plugging the value in for t, and the I component just gives you the x, or the I coefficient gives you the x component, the j coefficient gives you the y component, and the k coefficient gives you the z component. Yeah, no problem. Okay.